Thank you very much. It's good morning. I will talk about basically a class of degenerate equations. It's really broad a subject. If I think about it, it's related to many different kind of issues. But today I'm talking about the degenerate equation, mainly coming from several complex variables, and also to some extent coming from fluid dynamics. The maths come from math physics also. Let me. I will start out with warm up and some basic phenomena and some really strange things happens for degenerate equations. Then state the main theorem and maybe give you a flavor of the proof. So degenerate equation. Well, I first would say about what is non-degenerate. And anything is not degenerate would be regular. Say this equation is not degenerate. There are many good things about this, but all I'm talking about here is from analysis point of view. So if you look at this equation, why is not degenerate? This really the bread and butter of analysis. Is this Laplacian equation? First of all, it is a isomorphism between various spaces. For example, it's isomorphism between H2 to L2, also between this C2 alpha space to C alpha space is isomorphism between, say, at W22. I mean, you have to use some kind of boundary condition, and L2 or C2 alpha intersect with this thing. I mean, any boundary condition and C alpha. I mean, it's really good. It's isomorphism. So once you see that, you can do a nonlinear perturbation of this. You all have this kind of phenomena. And but from analysis point of view, it's amazing statement. It says that once you have, say, the Laplacian is in L2, you control not only the Laplacian, not only each term in the equation, you control the terms not even appear. I mean, this equation says a special linear combination of second order derivative is L2 or holder. And the conclusion says the isomorphism says that each of the term appeared in the equation is under same control because it's isomorphism. Not only that, the terms that not appear is also controlled. So it's like amazing statement. So this is a fundamental thing. But if you compare this equation with degenerate ones, you won't expect this kind of things. So what are the degenerate equations? So anything not that good, we say that degenerate. Let me write one really bad, and that maybe you can say the following. This can be written as a special case of Aij Uxi xj, and in that case, this Aij is this delta ij, right? And that's the positive definite matrix. If you do a change of variable, any positive definite matrix will work. But so what's a special positive definite matrix is has rank n, and the positive definite. So let's write this one. Say dx minus say y dz squared plus dy minus x dy dz squared u equals to f. And if you write this as a matrix, you get dx squared u plus minus 2y dx z u plus this plus and plus dy x dz u plus dy square u plus x square plus y square. So what's the thing that went bad is this equation, if you look at the determinant. So everywhere is determinant is 0, it's rank 2. So that's one type of bad equation. And I think in this workshop you'll see that this type of equations Laplacian u y minus say alpha u y equals to say fxy. I mean x can be any number of variables you want, and in this r and plus. This also degenerate. And also the equations from say nonlinear ones can be thought as degenerate equation also before you knew the determinant or the Hessian of u is positive definite. But once you know that's positive definite, it's become non-degenerate. And this kind of equations, divergence phi gradient u, say in fluid dynamics many times you have this kind of equations. It's very often appears like potential flow of fluid dynamics. So let me start from here. So observations. Let's say something really bad not happening. Let me assume, say, u is smooth. And also, let's take a really special one. Say, let's take alpha equals to 1 equals to, say, uy. I mean, this nice-looking equation, right? It's harmless, you know. And you try to, say, solve boundary value problem. You just say, well, actually, you can solve it. I mean, this kind of Dirichlet problem is always solvable. Excuse me. And you can also write like this. Suppose that the elasticity is a function comparable with the distances. This kind of things is always solvable. But let's see. Assume it's smooth. What happens? It's kind of bizarre. If it's smooth, of course you can allow y equals to 0 plug in, right? If you plug in here, you get uy equals 0. Uy at x0 equals 0 by the smoothing. Then if that is true, you have this equals uy over y. Then you can L'Hopital's rule, right? You take limit, I mean everything's smooth. You get uyy x0. And let me remind you what is Laplacian. This Laplacian in x of u plus uyy. So this implies that Laplacian of x of u, at least restricted to the boundaries, will be there. So what's the consequence? The consequence Laplacian x. I mean this equals the boundary data. Equals 0. So what it says is that if the equation is solvable by smooth functions, then the boundary data has to be harmonic. Otherwise, there's no way to solve it. And this is one phenomenon, kind of you have to keep in mind. The other phenomenon, let me start to talk about something not so trivial. Again, say this equation. Then you can see that u equals to y1 plus alpha is a solution. Actually, this I don't have time to talk about. This actually implies the Dirichlet condition, Dirichlet boundary value problem. I mean, at least for continuous ones, can be solved. If this function is continuous. So once you see a function takes zero boundary data in a nice fashion, that means the solution can observe the zero boundary data. Once the solution can observe zero boundary data, the solution can observe any constant. If the solution can observe any constant, the solution will be able to observe any continuous functions. So this is the analytical reason why it is. I mean the details actually, if you see this in a paper of mine with Fan Hua Lin and Wang, carry out all the detail. But that's basically the point. But his very fact actually means other things also. I want to compare this with Laplacian. So if you compare Laplacian equals to 0, everybody knows we have this Hofer lemma. It says if u is positive, then u is positive there, implies that, I mean, u is 0 there. For example, implies that the normal derivative is positive at the minimum. What that means is that, at least analytically, I mean, I only talk about the analysis, is that once you see u is a positive, this positive propagate, this information propagate immediately to the boundary. Not only that, it's influence the first order derivative on the boundary right away. Because if you change this positive things into a little bit more positive, then instantaneously you will see the normal derivative of the solution on the boundary change a little bit. So this basically says that all the derivatives of the harmonic function on the boundary depends on the interior data very, very well. The information start to influence the boundary behavior at the first order derivative. But look here. This, I mean, I might take alpha equal like 100. Okay, then you see that we observe this solution u is y to the 100 plus 1. So the Hofer lemma cannot be true unless you go to the 101th order derivatives. And people familiar with this equations with regular singularity, that's exactly the truth. For this kind of equations, all the derivatives up to that critical power is really, really elementary. I mean, you can just observe it because of this special solution. All the derivatives up to that 101 power, they are local information. The derivatives of the solution on the boundary is completely decided locally, point-wise, by the boundary condition. And at the level of 101 derivatives, those are global information. The information is coming from everywhere inside. So that's the a non-local thing. So that's two bizarre things. Then let me say this kind of example, say uxx plus uyy equals 0. You have this solution is again elementary is ux squared minus y. I think minus or plus is a solution. And the boundary data is, if you let y equal 0, it's half, right? I mean, at least say y bigger than 0, this elliptic. It's a nice looking equation. The coefficient is analytic and everything is nice, but you have this kind of bizarre solutions. Okay, it's enough bad things. So so the key breakthrough, I mean the fundamental breakthrough of the degenerate equation is actually due to Homander. He basically also Homander and I have to say Homander and Jiaokun. They all observed the following: is that if you look at this type of equation, or including this, is that let me go back here. It's why elliptic equation is good. It's because of the propagation of the information is in all directions. It's this each point from equation point of view, they treat it equally. No point is special than the other one. So all the values they negotiate, and the ending result is everybody happy. That's what elliptic equation means. And for this is there are directions. Is the let me use the Homander's language. Let me define this vector field dx minus y dz, and y equals to dy plus x dz. So this equation has a normal propagation of information in the direction x and y. It's just like a elliptic one. So you can pull up the coordinate in the wrong way. You see an equation, a perfect elliptic equation, which is elliptic in this direction and in that direction. So the information, they talk to each other pretty well. But there are deeper thing, is that if you look at the Lie bracket of these two directions, you have 2dz. So what's that mean? It means that the information can be propagated in the missing direction. So at 0, so x equals to dx, y equals to dy. So those are the controllable direction naturally by the differential equation. However, you have the Lie bracket at 0 is dz. So what the Lie bracket means that geometrically, if you follow x, the vector field, then follow y, then follow minus x, then follow minus y, you discover yourself you went up one story higher with smaller magnitude, but you did went up. So as soon as you went up, the information reached upstairs, reached the missing direction. And that makes this information, all the values start to talk each other everywhere. And that's basically the definition of this nice equations, This kind of phenomena is called subelectric. I should also talk about something really bizarre. If you look at the mean curvature flow formulation of a level sets or the conservation laws, it's a kind of an equation. It's elliptic only along the hypersurface. There's no information propagation whatsoever between the level surface. But if you put level surface together, they form a formulation more or less, because the maximum principle forces you to do that. Even they don't talk to each other. It's not the end of the world, but this are kind of a nice case. And the theorem by Homander is the following: is that this is Homander. If you look at the sum of vector fields, say 1 to k plus x 0, is hyperelliptic. If the Lie algebra, the out generated by this is xi xj, and finite many times generates the whole Rn. If you observe this phenomenon, not only this, you'll be fine. And for example, at this he cannot do this, but if you have y squared, then y squared, then this you have dx. You look at dy, will be fine. This is minus dx. So this generates whole tangent field. I mean, this two representing a phenomenon. By the way, I don't know. I haven't really talked with Homander. Recently, there are people working on equations called that parabolic or hyperparabolic? Oh, no, extra parabolic. I mean, for Homander is that all the parabolic equations, they are subelliptic, because you have Laplacian here, you have ut here, and they generate the whole direction. So he covered everything. It's kind of crazy guy. So let me talk about my main theorem.
The case, why Laplace U something equals something? Is there not the Radkevich-Olenek work for this kind of equations precisely, where you?
Pardon, what?
Is there not? I think there is some work by Olenek, Radkevich
Right.
about equation precisely why Laplace U equals something, such that it's not y squared Laplace U.
Yeah. You do, but you have to be careful. Say for example here, Yeah, you do. I mean, you can solve Dirichlet problems, but I say if you want you don't expect our solution to be ellipses, but Holder you could, because look at and you can manage it to do so. Once you observe this almost ellipses solution, then Holder wins.
But is there a general condition that could replace the nice Lie algebra condition?
Yes. That's eventually that's something I want. I mean this to answer you. I don't know yet. It's that so. So what's the question? The question I mean I want to talk about is that how far we can push what we observed for not so smooth equations. For not so smooth degenerate equations. This is a theorem with Shah and myself. Oh wait, it's kind of complex to state, but let me try to do it anyway. So let M be a 2n plus 1 dimensional a real manifold, real CR manifold of say C2 class. It's kind of hard to explain. I mean, it's so what's that mean? Let me then let box B be the Kung Laplacian. This can define on any PQ form. Then box B U equals F. Let's write it here. C2 alpha star. Moreover, or I mean, better smoothing. And I miss an important condition, provided there's a ellipticity condition. The YQ condition holds. On PQ. Okay, maybe I better don't. So let me say what is new. And the kind of also the historical reason. Actually, this theorem, why people are interested in this is to study the de-Bar-Neumann problem, boundary value regularity, and this is what it boils down to. And the first, I mean, all this is, I mean, Homander and at that time, and also Jiukong and they were trying to look at this problem, and this analytically, this is the question, and what the first breakthrough was, I think, Kuhn.
Can you recall the definition of Kuhn Laplacian? Yeah.
Kuhn Laplacian is you first define a d-bar, the d operator on forms, but along the tangent. If the CR manifold is defined a real boundary of complex manifold, you just take this d operator, then you this. It's really the Laplacian, and a typical example is just like that. That's one of the example of a box B operator. You have good directions and you have a direction missing.
What is the boundary here?
No, this not on the boundary. This can be thought as the normalized boundary, like a unit ball in C2, and the boundary 3 dimension. And 3 dimension, you have 2 directions go to 1 direction missing. That's basically the thing. So Jiaokong and Homander prove it for C infinity manifold. In the L2 category, in the L2 spaces. So you have resonance is L2. You have and H1. You have those kind of a gain of regularity. Then later on, Holland, Rothschild, Stein proved CK alpha star and WKP for C infinity manifold 2. I mean, I want to be fair. If you read the proof, you don't really need the C infinity compact smoothness. However, you need like at least like 10n. I mean, I just. But C2 is the minimum one. C2 is the minimum condition required for this level form, Levy form to make sense. And
so we have another stupid question. What is the star? Why is it
I haven't really said it yet. So there are good directions and the bad directions. Star means that you have a perfect control in the direction of equation only. Yeah. But once you have say the second order derivatives control only in the good direction, then you have the Lie bracket. Then you have the bad direction first order derivative automatically. So that's the. I mean this is the. Okay, and so let me. I don't have much time. Let me give you a flavor of the proof. The key thing of this two. Let me make another comment.
So the star would be like when you do parabolic regularity, you gain 2 derivatives in x and 1 in t. You would be
Exactly. Yeah. So this is the relays on singular integrals. On a nilpotent group. And what is that? Is actually relates on this. You look at the box B operator. You solve this like a third of function. Then you look at let me call that this. That should be Green's function. Then you look at xi, xj bar or whatever g, and estimate this in very precise fashion. And just by looking at this formulation, you need at least like 4 derivatives in order for the whole setting. Even you can talk about it. And I mean, clearly C2 won't make sense. And also, if you read the literature, there are lots of people working in this direction, and they are this is very, very popular subject recently. Or you put a star or not star, doesn't matter. Then suppose Aij is a kind of size of elasticity or AP waves, things like that. Then you have all the Holder-Harnack Poincare inequalities. But the thing is, I don't want to say, but I just say what happened is that they all assume, or most people assume xi, yj, they are nice operators. So it's really a problem. How do you go to the limiting? I mean, the equation you just look at this makes sense. How do you get this most reasonable estimates? So the proof. Let me sketch a proof of LP is LP and
Can you say a bit about what is YQ condition?
a YQ condition is you have to look at there's Levy form. I mean let me say one word. Levy form has enough. Let me say it. Enough non-zero eigenvalues. So basically is I think it's Jiaokong's. I mean I can write it explicitly. For different forms, you have different conditions. It's you need enough regularity condition to get the energy estimate. So once you have that, you can stop. Non-degenerate condition, yes. It's this if I write it down, this box B for different form is a bizarre, complicated equation. Yeah. So I really running out of time. Let me write a typical one, and let me do say 1/pi. Do a W1P estimate. Let me put a 2 here. The spirit of LP estimate more or less buried in this one. 2/pi is really 3.14. Just to indicate this example. So what's the difficulty is that if you look at this equation, the Hohmander's formulation or the singular integral, they both fail pretty badly, because you cannot even talking about the Lie bracket of these two vector fields. I mean you cannot compute this, right? I mean what is this? It's not. But the geometry of the equation survives. So the geometry is there's a singularity here as a bad direction, and the equation's value do talk to each other. It's if x is not equals 0, they propagate pretty well. Since they talk to each other pretty well, then the information from here to here, it can be propagated just away from this boundary. And more than that is that you have this kind of perfect scaling. It's Rx. I mean I tricked myself. It's 1 plus 1/pi y. Scale invariant. So if I define the UR of x, y, and I define this operator LU, I have LUR equals to, you do have R squared, then good things on the right hand side. Probably stretched. Okay. So the key point is that how can you prove a LP estimate in 10 minutes? So lemma 1 is pretty easy. Is that LU equals to say let me call that controllable divergence of F. Then this is everybody can compute it. This ball, say 1 plus x to the 2/pi x uy squared less or equals to f squared plus x 2/pi g squared. It's ball 2. This energy estimate. Then you do observe some regularity. Let me. There are other means. Let me use Hohmander. You can cheat. Use Hohmander. Say 2/pi is is 2.3 is less than 2, so I can say x squared uy squared, right? X is less than 1, by the way. So Hollander says this bigger equals to use h half norm squared. I mean, this you can talk about Lie bracket. There are other means, but this works. So you do have a gain of regularity in all directions, all the way across to the manifold of the singularity. So next, you want to show the goal is to show that if f of g is in L pi, you want to imply ux equals to L pi, and x 1 over pi u is in L pi. That's what you want to do. And this is exactly the heart of the matter of harmonic analysis. Is a difficult thing to do. But you observe L pi, or even L2 norm is not that easily geometrically observable. You better ask yourself, what do I mean by L2? So L2 is actually the best understanding. You shouldn't understand by naked eye. You should understand like quantum mechanics. Is L2 is not, say, I draw a picture, say that's L2. That's not the way of understanding it. The way to understand a function is L2, or say L2 norm equals 1. You better say this. You better say lambda, u bigger than lambda. So that is that. Is that right? So what does it mean? You have to, and there's only correct way to understand it, is that the probability for ux bigger than lambda, the probability is like 1 over lambda squared. And that's the only way and the only correct way. You can say that's this silly inequality. You can improve it, but improve it log. It's beyond naked eye can see. Okay. So now, our goal is to show the like intrinsic gradient of the solution is in L pi, and the condition right-hand side is L pi. And you can really do it. But now, once you observe that, the understanding of the regularity is I think much better in a way that in order to show something is in L pi, you don't want to show it's L pi. You want to show that you run them to the point. You have much better chance for the gradient to be finite. If you can see that, you are done. The probability for the gradient to be huge will be small according to a controllable fashion at the right-hand side. So before you do that, you ask you another question is that, do I have any chance at all to find a good point of the gradient to be finite? And this is the first lemma, and you do, is that.
Sorry, what's the significance of why is it clear that you should try to get L pi? I mean,
No. This is just an example of the proof. I mean, the pi is just a random number.
But I mean, if the pi's here, I mean, what's the connection between the estimate you want to prove there and the
This is I just put a special case for x for p equals pi, and then let me work on p.
Well, no, that's okay. But I mean, so you look at the equation, you automatically can see what estimate is the key estimate here.
No. Right now I want to prove. I mean, you can prove Wick's solution easily. So the question is that if you have an increased interoperability of f and g of right hand side, how can you prove the corresponding regularity of the solution?
I think the question you're asking is that the pi over there has nothing to do with the pi over here.
Yeah, I better take e there.
You put E.
Yeah,
Oh,
e.
okay.
Right.
That's right.
Yeah. Right. I'm sorry. E. Yeah. Right. Just some random number. Yeah. I won't work. So okay, now I say you throw a dice, you wins. Because what's that says the gradient in L2, you randomly choose a point, you are going to see gradient is finite. However, that's not the best thing you can do. If you do throw a dice, you have much geometry you can observe. You are not only land a Lebesgue point of gradient, you are land a finite point of the maximum point of the gradient at that point, with 99% surely is finite. So the maximum function of ux, I mean, is ER of 2 over pi. Sorry, I don't want to change this. This is in L1 out. This is in big L1. Namely, exactly this is big L1 means what? There you have basically no chance to hit pointwise of this function huge. In other words, most of the points you will see that this is really dramatic is you are for all the r's. I have to talk about intrinsic r's. Will be finite. Say less or equals to lambda with exception 1 over lambda squared. Right? It's like that's.
Ux squared plus the whole thing.
This is actually soup of R. Also. Soup of. I'm sorry, I did this. Uy squared. Average. This should be inside. You do see very nice picture. Then this is basically nothing. This is the maximum operator estimates. Then next you argue this is that if L of u equals to f is small, then this inequality fails with amazingly small measure. Then that the maximum operator of ux squared. And then exact one. So this would be the key estimate. There's almost no, in the case f is small, this f is small. I want to say the probability for gradient of the solution to be huge, almost 0 probability. And this says that infinitesimally you gain the integrability of gradient. Then then you write this by current lemmas, you get this gain of integrability of right hand side. But this I can prove like in 1 minute. It's really easy to do. And this really, and you see that there's no singular integral. You don't need any smoothness whatsoever. So why this is true is that whenever you see this major chunk of the solution is nice. So let V solves, I mean I cannot do this. It's like you run a compactness argument. In this case, there is a V smooth to the certain extent. Let me just say ellipsis solves LV equals to 0 in ball 1, and LU minus V equals to F, with the L2 norm U minus V is as small as S1. This is a typical compactness argument. But they are really tiny. So this, then you use this lemma 1, or I didn't ordering it. So you get this the difference of Ux. Let me just compute this term. Ux minus V x squared would be really, really tiny. Now, No, this is bigger or equals to, if you localize it, it's bigger or equals to say lambda. There's there's a huge constant by the maximum functions. The maximum function of u minus v x squared bigger than lambda in Q. I mean, I cheated a little bit. This is the typical maximum. But if you further localize it, inequality is still true. But then you observe that the maximum function of Vx in Q half or in ball half, this bad to switch letters, is a fixed constant, right? Because they are ellipsis functions. So if you take lambda, be that number is bigger or equals to, so take lambda huge but reasonable, you get this x equals to 4 half. This is, as I claimed, say 4 half. So you observe that whenever right-hand side is small, you have amazing assuredness for the gradient of u to be bounded. And that very statement says that you increase the chances for the gradient u to be small. And of course that says LP. You just write down this balls, choosing in the correct way, use Vitali, then you get this LP estimate. So let me stop here.
Last step means you're interpreting.
No. You can really do the computation,